This video relates directly to the CIE, IGCSE and computer science. It is about data representation. Of course, it's applicable to all GCSE specs. So to start with, there are three types of number system that you need to be familiar with and to be able to convert between them. That's binary, often known as base 2, denary, base 10, and hexadecimal, which is base 16. And of course, they each have their unique characters that are used to encode the data. So first of all, why do computers use binary? And one clear answer is due to the electronics that are used on a computer, the switches, transistors. And because currently we do not have the technology to create switches that can reliably hold more than two possible states, on and off. Quantum computers aren't exactly for sale at Currys at the moment, and so the binary system is chosen because it's quite easy to distinguish the presence of an electric current from the absence of electric current, especially when you're working with trillions of such connections as you will on a processor or other electrical equipment. So that is the main reason. So if you see here, base 2 is often represented on a scale that often reads from right to left, which can be counterintuitive. So for example, if I was to choose a number such as 27, how do I make that represent that number in our normal base 10 number system in binary? Well, of course, simplest method is to start with looking at the highest number we can. So 32 is bigger, so can't place anything there. Next one is 16. Now 16 does go into 17, so we'll drop a 1 there, and that leaves us with 27 minus 16, which is 11. So 11 now does go into 8, so we'll place a 1 there. That leaves us with 3. Now 3 of course is smaller than 4, so we can't place a 1 there, so we'll place a 0. 2 does go into 3, so we'll place a 1 there, leaving 1, and of course that then makes our 27. Now if we need to represent that in 8 bits, we can just pad the zeros this way and just put some zeros there, because they've got no meaning. 0 is just a placeholder. They do have meaning in the sense they're a placeholder, but not in the sense that they're a value. So they're important in some respects as to read the magnitude of the number. Because of course, if you took what we've just put there and moved everything one place to the left, then of course the number will double. Move it across again and the number will double again. That's due to the nature of how binary numbers grow. And of course we've got the implied binary point here. So base 10 of course works in a similar way. So we go from 1 to 10 to 100 to 1,000, 10,000 and so on. And of course we place a 1 here, it's worth 1. We know that. If we move it across to here, it's worth 10 and 100, so that we know that 111 is 111. But if we shift all of that along, and I'll represent that with purple, then we'd have 1, 1, 1, which would be 1,110, which is 10 times greater. Just similar to how I've explained it in binary. When we move across left by one place, we double the number. But in our number system, base 10, not just double, we times it by a magnitude of 10. So let's have a practice at some binary here. So 27. It helps to have a framework like above. So I'm just going to place, the largest number is 52, so I'm going to have 64. I'll use this for all of them. 32, 16. And this helps in the exam so you don't make silly mistakes, which are more likely to be the case than calculation errors. So 27, let's remember what we did. So 16, that leaves us with 11. 8 goes in, that leaves us with 3. 4 doesn't, 2 does, and 1 does. and we can just pad it if we need to make 8 bits. So 1, 2, 3, 4, 5, 6, 7, 8. Then we move on to 3. Obviously it's going to be 0, 0, 0, 0, 0, so it's going to be a 2 and a 1, and then we can just pad the zeros. 19, what's the biggest that goes in? 32 is too big, so we're coming at 16. Then we're left with just 3, so it's a 0, 0, a 2 and a 1 that make 19. So obviously we're just making up the numbers. A good way to practice this is binary blitz. If you Google this, it's a fun little game you can play just to make sure you're really crystal clear on how it all works. Finally 52, 64 is too big, so we go in at 32, that leaves 20, 16 goes in, that leaves 4, so 1, 0, 0. The other thing you can notice to check as another way to validate your or to verify that you're correct is if it's an odd number, you would notice that an odd number will have a 1 here, of course. If it's an even number like 52, that should, the final number, as I've illustrated here, should be 0. So just look out for that as well. Also useful to know, not for this spec but for other specs, it's fairly straightforward, is that if you have 8 bits, you can choose how many you store the representation of the whole number compared to the fractional element. So for example, if you wanted to store 6.5 below, then you would have a 1 here, 1 there, so that's 0, 0, so that represents the 6, and 0.5 would be a half. And you can see how the fractions, instead of going up and doubling, they halve each time. So you have a half, a quarter, an eighth, a 16th, and so on. And so that would be 6.5. And if I wanted to represent a slightly larger number, for example 13.75, then of course I'd have an 8, then the next would be a 4 to make 12, and a 1 to make 13. 75 would be it's a quarter plus a half. And of course you can expand up the fractions below in order to add them. So for example, what I mean by that is to do it by hand. A half obviously is equivalent to 2 over 4, so that you have the same common denominator. So that would be obviously 1 over 4 plus 2 over 4, which would be 3/4, 3 over 4. So you can expand to whichever the greatest common denominator, which could be over 16 or over 32 or 64 as you go. So let's look at how the numbers grow. So if you only have 1 bit, you can represent a 1 or a 0 in our traditional computing system. 2 bits gives you 4 possible combinations, as you can see, and 3 bits gives you 8, 4, 16, 32, 64, 128, 256, 5112, 1024. So you can see that they double with each bit. So every bit we add, we double the number of combinations, and of course it's these combinations that we can use to encode the data as either text, colors, numbers, etc. These are the basic representations. And you'll notice these numbers in your home in terms of SD cards, iPhone, Android phone storage capacities, often 32 or 64 gigabytes. And that's due to the binary nature of how the storage medium works in terms of the maths. So just a quick look at sort of the processor, main memory and hard disk in terms of the amount of storage. As you'll see advertised on Computers for Sale, right close or on the processor you've got the cache registers, really fast storage, often 2 to 8, maybe 16 megabytes, and that's broken down into level 1, 2 and 3 cache. So level 1 is closer, you usually get less of it. Level 3 is not as close, relatively speaking. So the more of that, the better. That helps performance of your computer. And of course, RAM, common now is 4 or 8 gigabytes. Obviously, you're going up to 16, 32, and 64, etc. This is fast. Different types of RAM, but some of the fastest RAM, of course, the Xbox One X has 12 gigabytes of RAM, because it's storing a lot of data about the images, for example, for an Xbox. But for your average PC, probably 2 to 4 gigabytes is going to be minimum. And then, of course, the hard disk, slower still. And these, obviously, depending on whether it's solid state or magnetic hard disk, will store anywhere in the gigabytes to terabyte range. So a lot more storage, but not as fast. So I've kind of drawn a graph below here to kind of represent that as you go away from the processor, the speed at which the data can be read and transferred decreases as we currently speak. Okay, so going the other way, what are these binary representations in denary? So let's have a go at a couple. So let's have a go at the first one. So we've got a 1 plus a 2 plus a 4 plus an 8 plus a 32, which is 32 plus 8 is 40, 44, 45, 46, 47. And then if we look at the next one, we have got a 4 plus a 1, which is 5. Then we've got a 4 plus a 2 plus a 1, which is 7. Next one, 15. And then the next one is 8 plus a 2 plus a 1, which is 11. Okay, so again, notice the last bit. If there's a 1 there on the right hand side, then that indicates that that is a odd number. Okay, now coming down, you're going to have to convert between the bases. So let's have a look at converting between hex to binary to decimal. Often good to go from hex to binary and then into decimal, because of course hex is just a shorter version of binary. So you think of it as expanding hex to binary and then to read the number in decimal so you get the correct number. Okay, so hex is just a short version. So for example here, hex is represented from the characters 0 to F. So 0 represents 0, 1 is 1, 2 is 2, all the way up to 9. And of course 10 can't be used for 10 because 10 is a 1 and a 0. So that's 2 different characters. So you need one single character. So we borrow the alphabet, the English alphabet, and use A for 10, B is 11, all the way up to F for 15. So that gives us 16 different states or combinations. So if we had to be presented with something like this, F and A in base 16 or hex, then what we'd do is we'd just draw a box with 4 spaces, which represents the F, and then we'd represent F, which is a 1, a 2, a 4, and an 8. So F obviously is 15, which we can look up if we looked up that from hex. And an A, as we know, is going to be 10. So if we look at 10 and make sure that we have done this correctly, let's just check A. So we know A is 10, so it's going to be a 1 and a 1, like this. Now if we put that together and then put the numbering across, and what I mean that we go from, let's just rub this out, if we go from 1, 2, 4, 8, so that'll see A is this, and then we put them together in that order, and now the order is important, of course, so we keep the FA and not AF, so FA is going to be this, and then we just number it all the way across, and then we add up all those values, and then we arrive at the decimal figure, which is base 10. Okay, and so let's look at this one. We've got 8 bits represented like this. So what we'll do is, let's get rid of these end markers. So we have a binary number. What we'll do is start on the right hand side. Okay, so you want to start here, work our way left, and just sort of block in every 4 bits like this. So 1, 2, 3, 4 block, 1, 2, 3, 4 block. And then what we'll do is we'll then add the numbers below. So 1, 2, 4, 8, 1, 2, 4, 8. Then third part is to then work out what the numbers within these groups of 4. If you're not sure why we're doing it every 4, that's because 4 bits gives us 16 possible combinations, which is hex. So a 1 plus a 2 is 3, plus that is 11. And we need to convert that now into hex. So obviously that's going to be B. Same here, we've got a 2 plus a 4, which is 6. And 6 is 6 in hex. And so we arrive at 6B, which is 107 in decimal. And it's 107 because, remember, we put the short version together, so 6 and B together, and then we write the numbers across the top, which I'm highlighting in green, to get the full actual magnitude of that representation, not just the shorthand version. So again, here we've got another example, but this time we've got 11 bits. So what you have to do is to pad it and put some zeros on the left hand side. It's important that you pad it on the left. Remember, if you padded it on the right, you'd push the number to the left and thus increase the magnitude of the number. So put the 0 on the left to make it up to 4, and then of course same process again, just write the weightings below, and then you can convert. So we have 13, 8 and 2. So 2 and 8, or 2 and 8. 13, of course, we need to replace with a character which is C, I believe, not D. And so that's the hex version. And then for the binary, working out, sorry, the base 10 version, we have to put the numbers which I'm highlighting across in green, and then add some big numbers together. As you can see, when you start to go to sort of 3 hex numbers, you can see you're going to be in the numbers you're going to be adding are quite large. So that's the conversion. And of course, let's have another quick practice on this one. Let's have a look. As you can see, binary here, split it in half,